Hi, everybody. Welcome to today's webinar, Dual Fuel Heating Systems, Advantage or Compromise. I'm Joe Wachunas with Electrify Now, here as always with the founder and my teammate, Brian Stewart. We have a great program for you today. We will introduce our esteemed panelists in just a second, but thanks for joining us. And we always invite folks to put in the chat box where they're tuning in from today. So go ahead and if you feel comfortable, let us know where you're listening in from. We are Electrify Now, an all-volunteer organization that believes that electrification is the quickest and easiest path to a decarbonized world. We boil our message into four clear and easy steps. Number one, clean up your electric supply through rooftop solar or community solar or your utilities green power program. And then number two, electrify your home. Today, we're going to be talking about a big source of emissions from the home, the gas furnace. But we have videos on our YouTube page on every sort of technology that will help you electrify your home. We'll talk more about that in a second. Number three is electrify your ride. We'll talk about our upcoming webinar on e-bikes to help you do that. And then number four is electrify everyone, to extend the benefits of electrification to those with limited resources. And on that note, thank you to all of you who, in signing up, donated to our nonprofit for this year that we're collecting donations for, Seeds for the Soul. Seeds for the Soul takes donations and helps to install solar panels and other electrification technologies such as heat pump water heaters in low-income households. We've raised hundreds of dollars this year so far through our webinars for Seeds for the Soul. So thank you so much for donating. A huge plug to our Electrify coalition. These are over 54 nonprofits that believe in electrification and are working towards an electrified future. If you're interested in joining, email Brian or I. There's no cost to joining this group. And again, a big plug for our upcoming webinar on August 9th. E-bikes will change your life. We're going to have Professor John MacArthur from PSU and Joe Boris from Clean Technica to talk about electric bikes. I just got one myself, and they're amazing. And then want to plug all of our Electrify webinar recordings. We have over 50 videos on our YouTube page, and we just exceeded 1,000 subscribers. So go to either Google YouTube Electrify Now, or you can see the address there on your screen. Okay, Brian, talk to us about dual fuel heating systems.
Okay, thanks, Joe. And a lot of people have been asking me, like, why are you doing this? In fact, some of them were even sounding a little critical that we would be talking about this, because normally, from us, we're talking about all electric solutions. But I think, first of all, I just want to say it's not necessarily that we're advocating these things. We just think it's important to dive into the facts about these systems for a couple of reasons. One is there's a lot of these big systems being installed right now. And for various reasons, some good, maybe some not so good, but it's a reality. They're going in. And here in Oregon, Energy Trust of Oregon, which is our efficiency organization, is considering incentives for dual fuel heating systems. So we thought it was really important to understand everything about these in terms of the practical considerations, which might make them look attractive to homeowners, because that's a reality. The real differences between them in terms of performance, and of course, the real differences between them and all electric systems and gas furnaces from a carbon emissions standpoint. So that's what we're going to be talking about today. We've got the perfect, I think, set of panelists to help us to dive into this topic in detail. And just a reminder, heat pump systems, generally speaking, come in two large versions, but of course, there's lots of permutations here, and you'll hear more about that later. But all of them, of course, they're going to have this external heat pump unit that's connected with refrigerant lines to, in the all-electric situation, what's called an air handler, which communicates with that external unit and is moving heat either into the house or out of the house. And then in the dual fuel situation, that same outside unit is connected to an evaporator coil, which is attached to the gas furnace in the house. And in this situation, the gas furnace is either just blowing air through that evaporator coil in heat pump mode, or it's igniting to provide backup heat in the situation where the heat pump can't handle the load on its own. It's important to note the all-electric systems sometimes take advantage of backup systems also, which are electric resistance strips, but many of the new heat pumps that are available today don't need that, particularly in our relatively modest climate here in Oregon. But these are the two major kind of systems that we're going to be talking about today. And of course, we'll be going into lots of detail on that, but I just wanted to help out with some nomenclature at the beginning. All right, so we're going to start with kind of a practical conversation about the things that affect heat pump design. And this is for a system for a home. And this is where, you know, the rubber hits the road, and we've got the perfect person to talk to us about that, because every house is different. And so there's a lot of considerations that go into designing the best system for a home. And in some cases, is it true that dual fuel could be a preferred solution, maybe a lower cost or easier to install or something? We'll talk about that. We'll talk a little bit about this set point temperature, which is a really important issue with dual fuel systems, because obviously you can either, in a well-designed system, the heat pump is doing essentially all the work, and in one that's not so well designed, potentially the gas furnace is being used a lot, and that'll have a huge difference in terms of carbon emissions. And then, of course, there's this situation that a lot of us are familiar with, that as the world gets hotter and more people are interested with air conditioning sales, central air conditioners are going through the roof. And of course, a lot of us would agree that it would be better if we were selling heat pumps rather than air conditioners. So we're going to talk about the differences there and why it's actually getting pretty close to attractive to just get rid of air conditioners altogether. That would be great. And then, of course, we'll be talking about the relative cost differences between these various systems that we're discussing. And then I'm really excited with the panelists here to help us dive into this complicated issue about greenhouse gas emissions and comparisons between, of course, gas furnaces, standalone gas furnaces, but also comparing those to dual fuel systems and all electric systems. We'll talk more about that in a minute. And then all of this, I think, is going to give us a much better background to have a really informed conversation about the role that dual fuel systems should or shouldn't play in our quest to decarbonize buildings, short-term and long-term. So that's kind of the program for today. We have lots of information. Our guest panelists are fantastic. We're going to start with Zach Turner from Comfort. He's a comfort advisor at Climate Control. It's a company, installation company, HVAC company here in Portland that we do a lot of work with. We like working with Zach because he's got a lot of experience in this industry, but he really takes this sort of home as a systems approach, really understanding all the factors that are important to help make sure that the systems are operating well and that homeowners are getting the biggest bang for their buck, and that they're comfortable and healthy. He's really experienced with these next new generation of high performance heat pump systems, which give all these advantages to homeowners to address those comfort and health issues. And I love the fact that he's just really, he's a practical guy. You're going to get a sense of this. He's the guy who's going to make sure that the clients are happy and comfortable, and is not, spending too much of their money if there's a lower cost solution that will work for them. So I think you're going to get a sense of the real practical considerations around heat pump installation from Zach. Then we're going to hear from two researchers from UC Davis, Teresa Pistorchini. She's the engineering manager at UC Davis Engineering Efficiency Institute and the Western Cooling Efficiency Center. I'm super excited to have both she and Subhajit, who I'll introduce in a minute, here, because they've done what I consider to be the most sophisticated comparison of gas furnaces to heat pumps. And now they've included dual fuel research that they'll be talking about today. And it's going into all the details about every factor that you might need to consider to really do a thorough analysis of the comparison of these. You'll get a sense of that when we go into the research. But Teresa has 15 years of experience researching building energy efficiency and HVAC systems. And she does this through laboratory and field experiments combined with building energy modeling. And she studied methods to decarbonize buildings and improve efficiency, thermal comfort, and indoor air quality using HVAC technologies and controls. She's got a master's of science degree in mechanical engineering from UC Davis. She's a licensed engineer in California. And I didn't realize this, but she's also a PhD candidate in civil and environmental engineering. So she's got a lot going on. And I appreciate her joining us today. And then her colleague, Subhajit Chakraborty, is an R&D engineer at UC Davis Western Cooling Efficiency Center, also involved in this research that I'm talking about. And he's got 8 years of applied experience with thermal energy systems, electronics, cooling, absorption, refrigeration, and building HVAC systems. He is also working on focusing on this building decarbonization through testing, modeling, and optimizing controls of HVAC systems. He was formerly a technical lead at Carrier Corporation, so there's kind of a Carrier vibe going on. You might have noticed that in the images I showed. It's not that we're like trying to sell Carrier, but they're a good partner of ours, and they've got there's a lot of good information here. And Superg's background is partly also at Carrier, developing commercial chillers and heat pumps, and he holds a master's degree in mechanical engineering from Georgia Tech, and he's also a licensed engineer in California. And then for the Q&A, we're going to be joined by Chris McKinney. He's the ductless VRF manager at Refco Inc. They are the Pacific Northwest distributor of Carrier and Bryant products. Chris has lots of information. He's been a really go-to source for me. He's got a really rich background as an installer himself, owning a company that installed HVAC systems. He's worked for Carrier in their heat pump division as a project manager, and now he's the VRF manager for ductless systems in all the Pacific Northwest, all the way up to Alaska. So he's got a lot of wealth of information about this topic today, and so he'll be joining us for the Q&A. All right, so we're going to start with Zach. I'm going to turn it over to him now, and Zach, you can start sharing. Thank you to our panelists, and also maybe just a reminder to our audience, if you've got questions, please put them in the Q&A. We'll do our best to kind of monitor that, but if we don't get to you during the show, we will have some time for Q&A at the end.
All right, thank you. Thank you for that introduction, Brian, and thank you, Joe. Thanks for having me here today. And my background certainly is estimator and comfort advisor for a residential. I'm completely on the residential side. When people know it's time to change out their equipment, that's when I show up and hopefully can steer them through the options in a way that makes sense. So today, dual fuel advantage or compromise. I'm just Brian walked us through the equipment examples. I have a diagram of this heat pump as a system, and I'll talk to you about how I think about these and design for comfort and efficiency. We'll look at what the heat pumps can deliver and some practical considerations. So here's my diagram. And what I like to show is all the components of the system, starting from the home, and then this is moving the BTUs. So the heat energy is measured in BTUs, of course, and it's first moved with the air system and then transferred over to the refrigerant, to the outdoors, and then released. This diagram is showing the heat. This is running in air conditioning mode, right? We're taking the heat and we're taking it from the house to the outdoors. And the magic of heat pumps is that they can go the other direction, but an air conditioner is a heat pump system that only half works. So I want people to get on board with a fully functional heat pump system. And the first component in this system is absolutely the house itself. So the first question I'm asking is, how well does this house separate the indoors from the outdoors, and how well does it hold heat? So with that, I'm aiming to help people be comfortable in their space. And the byproduct of that is these getting the equipment to run in the most efficient way that we want to. So I'm designing to condition evenly through the space. I want quiet performance. I want to put that heat in slow and steady so that we feel the radiant, right? I affect the surface temperature of the space. I'm not looking for blasts of hot air that satisfy the thermostat and have temperatures going up and down. There's also humidity controls, a lot more important than other parts of the country, but it does make a big difference for comfort for us. All of these are achieved. A house is, I make a comparison to charging a battery, where if you try and do a fast charge, it works, but it doesn't really stick. It's not a deep charge. What I want is to put that temperature into the space so that air is moving, spreading to the far rooms. We have air circulating, so we have more even temperatures, less stratification of upstairs and downstairs. And we accomplish with that these efficiency goals: peak equipment performance, gentle run cycles, lower energy bills, cleaner operations, and a longer equipment life. So I just will point out that the key feature of, if you're looking to buy a furnace, you look at an advanced furnace. The best furnaces out there, the main feature that makes them better furnaces is their ability to modulate down to a much less than full capacity. So they work more like a variable speed heat pump. When I am at somebody's house, of course, I'll do all my measurements and focus on the equipment, and then I switch quickly to focus on understanding the home. This is an example of, right, we have a lot of inputs. It's a computer program where it's pretty quick, but it's really important to look at how leaky the house is, what kind of insulation they have in the attic, walls under the house, what's going on with their windows, and really importantly, the duct situation. So I can input it into software. This is called a manual J-load calculation. And what it gives me are really clear numbers. I love that it's right. So in this sample house, it's saying the amount of heat we need to pump from indoors to outdoors on the hottest day is 30,000 BTUs. So 12,000 BTUs is a ton. So that's a 2.5 ton system for cooling. And it's saying 47,000 BTUs on the coldest day in our region. We need to bring in 47,000 BTUs to keep this house comfortable. That's close to 48,000 or 4 tons. So it might be tempting at that point to say, hey, we need a 4-ton system and we're done. Now we know what we need. But there's a little more to it. And I want to focus also on the, I'll come back to that ductwork here because the question comes to mind, can we move enough air? There's, of course, a direct relationship between the air temperature and the amount we need to move. So I want to come in slow and steady. I want to be working with more modest temperatures, and the average heat pumps are good heat pumps. The average temperature that we're getting is a comfortable, say 109 degrees, but a little bit less than furnaces where it might be 120, 125. So it's completely matching what I want from a design standpoint to make the system more comfortable and also get better performance. The other point about air, so I mean, this is at a really practical level, looking at how many ducts do I have and are they big enough? And besides, are they leaky, but are they insulated? Most ductwork is subpar. And not only is it how much can we put the right amount of air at the right temperature in the right places in the house, but heat pump performance is really dependent on good airflow. So when you actually look in the performance tables, they'll have numbers of that it can deliver this much heat at these temperature with this much airflow. Next, I'm going to look at the equipment and what the equipment can deliver. We do that with these performance tables. This is I'm using a 3-ton as a sample unit to look at. So this chart is for a 36,000 BTU rated heat pump. And this top line is showing what on the left, it shows thousands of BTUs. So, and at the bottom, it shows the temperature. So you have 0 degrees over on the left and then over 70 degrees on the right. So if in the warmer temperatures, this 36,000 BTU rated heat pump can deliver, 46, it's delivering well over its capacity. And that's down to some pretty cold temperatures. So this top line is all the heat pump can deliver. This bottom line that's dotted is showing the minimum capacity. And I want to be, that line is where we want to be, right? So if maybe we need to come in with the maximum to get the place to temperature, and then I can ride at those lower temperatures where I get the better performance, better comfort. I've added this green line so that the red dot on the top left, that's when I do my load calculation, right, it's saying the extreme. So I've got at 17 degrees out, we need 47,000 BTUs. That's what I have marked on this, 17 degrees. And so this line, my red dot here is obviously above what the heat pump can deliver at that temperature. And so this is really what this presentation is about is, what's our solution for this gap at the times when this green line is what the house needs. On the coldest day, we're up here when it's 65, 70 degrees out, the house doesn't need any input from the mechanical system at all. So in this system, these lines cross at 26 degrees. The heat pump has capacity to keep the house conditioned down to 26. So that would be our crossover point. That's when the heat pump says, hey, furnace, you take over. Or we have an all electric system where the furnace, that heat pump can still do really most of the heating, but it's going to need some assistance. I've added a little bit of data to the same chart here to show kind of the relative importance, or how I think about this backup or auxiliary amount. And what I've added is this yellow line here. And when I start to do a load calculation, it gives me a temperature, the 99% temperature. It's saying that 99% of the time where I am, it's above this temperature. And if you look, it's 29 degrees where we are. So this whole discussion is really about, 1% of the time it's colder than our capacity with this heat pump. The other thing that I want to point out is just to emphasize that importance of the ducts in the system. Here I had, if I counted up all the ducts and said, boy, I can move 1100 CFM of air. So we measure air in cubic feet per minute. So if I say the airflow is enough to support 30,000 BTUs, 2.5 tons, then even though the equipment has the capacity to deliver a certain amount of heat, I'm limited by how much heat we can actually get into the space at that temperature. So I have a realistic crossover temperature here at 30,000 BTUs. And so instead of a crossover temperature of 26, it would be here at 34. And they'd have a choice of whether they could fix their ducts or help the ducts, which usually is really difficult. Or you say, hey, 95% of the time where the heat pump is taking care of business. And let's see. What I wanted to give here are two examples, or this is an example of the same heat pump. So the same outdoor unit. This is a great modulating 3-ton heat pump. And all of these, what I've done is I've shown the same outdoor unit in two different configurations. So we can compare the all electric version on the top with the dual fuel version of the same heat pump system. And I've outlined in green the key performance metrics on it. My point being, if you look there, this is the cooling performance, the CO2, this is electricity usage and heating performance. We've got the same system really. So I am less concerned about what box pushes the air around. My goal is to help people get into a good heat pump system. But you'll see here, I also circled this number over on the right because the CEE1 translation is, if you have a yes in this category, that means your equipment qualifies for the $2,000 tax credit. So that's an important thing. I've got another example here. This first example is the large traditional style heat pump. So it's a pretty big outdoor unit. The second one is that mini split style. And here's, I'm a Carrier dealer, so I'll say they really have some fantastic, there's such a variety of options and a number of these categories when we're going all electric or high performance or cold weather heat pumps. I think they have some industry leading stuff. This one is a mini split style, so a lot quieter, smaller footprint, easy to combine in all these different configurations. And I'm going to show you that these performance numbers with the all electric, and this is just for this particular size example. I wanted to show that these performance numbers are not the same. So in the dual fuel scenario, the performance isn't quite as good. It's fantastic, but it's not the same as the all electric. And then so a little difference in performance over here makes a big difference in the decision making matrix, because the all electric one gives you the $2,000 and it's dual fuel. We need to hunt for either you come up with a different configuration, because there are dual fuel ones with this type of unit that do qualify, or you say, you know what, we're going to choose the unit that is the best match and forego that tax credit. So in my mind, when I say why dual fuel, the first thing is that, hey, this is still a high performance heat pump system. So it might just be easier and certainly less cost, or in some cases less cost. I want to say certainly because oftentimes it's a wash, or you can come out better on the electric side. But there's a scenario where, say somebody buys a home and it has a 3-year-old furnace, but they know that doing a heat pump is the right way to go, or they're just ready to add cooling. So definitely to go the heat pump route instead of AC. This is a good option. Sometimes it comes down to which box with a blower will fit in the hole. It's just that at this point, the main difference is that with a furnace, we can generally come into the side of the furnace. So it takes less height for the overall configuration. And an air handler, it's the same as a furnace with a coil, except we have to come in either from the below or above. And so it might mean, well, I'll have some examples to show this. It could be that your electric panel doesn't have capacity. Some homes are just so leaky, they need a constant flow of high temperatures for a lot of the year. And then the last scenario I'll mention, I have some people that have said, well, I want my house to be able to run on a generator. And I've had cases where the generator could run the fan on the furnace, but not a whole heat pump thing. So it comes down to really practical nuts and bolts reasons. And so I'll illustrate a few of these with examples. This home is one where they had the furnace in the middle. It's a 12-year-old furnace, and I encouraged them to replace the whole system. They said, you know what, we might get, well, they were very optimistic about the number of years they were hoping to get out of it. So we said, all right, well, let's add a heat pump and it will work. When we opened it up, what we found is that the heat exchanger was toast. It was, obviously cracked and unsafe and needed to be replaced. So they were happy to learn, to know that and not be living with that situation, which was totally unhealthy. They ended up doing a full replacement. So I guess my point there is that when you're looking to keep your existing furnace and add a heat pump to run it, it's really going to be for newer furnaces. In 2019, they changed to a different style of blower that uses a lot less electricity. And those are the systems where it makes sense to add a heat pump. This next example, this house, just see that in the back of this house is all outdoor living space, and there's not really anything on the sides. And then the front of that lower story has a rock facade. The new owners, right, there's a for sale sign. They bought this house and they want to add cooling. They wanted to add cooling to the house. So they asked for a high efficiency furnace and an air conditioner. And so I heard them say efficiency right off the bat. And so told them about heat pumps, and the high efficiency furnace part, that would involve changing the venting. It was going to open up a whole construction can of worms, because we have to now go to a PVC vent that needs to come out one of those walls or up through. It just wasn't really a good option. So here they have, I also want to, they have a really great heat pump system that's going to do really all the heavy lifting. And they're using an 80% furnace as the box to run that heat pump system. I also want to show the nice form factor of this unit, that if you look at the house, it's to the left in our view. It hugs up the wall and it allows access along the side of the house. So some of these new some of these new heat pumps are great in that regards as well. This next example, this furnace is buried. So the middle is what I found, and this mechanical closet is deep inside underneath this house on the lower story. So there's finished living space above it. There's finished living space all around it. There's no way they were going to change their venting to high efficiency. But we're able to, and also the air is coming into the side of this furnace, and there's definitely no room to lift this box up and go with an air handler solution as that is available now. So, but on the right, you can see that they have a high efficiency communicating variable speed heat pump that's going to do a fantastic job of keeping them comfortable. This next example I wanted to show relating to the electrical. These people were doing a number of upgrades to the house, and they had this very old furnace that they wanted to get rid of. And they were from the get-go, they were on board with electrification, wanted to go all electric, excited about it. I opened up the electric panel. I saw all these empty slots at the bottom, thought fantastic, we're good to go. But then I saw that this was 100 amp main here at the top, and they've got 50 for a hot tub. And once we added this all up, we saw that they were actually really over what this panel could offer with existing equipment. So the other factor is this is a buried electric line in it. So it's not just a question of a panel change at the panel. It was going to be $6,000 to bring in a bigger electrical feed. So I explained that to them, let them know what we were looking at, and they said, we have other plans. We want an electric car, and they were fine with that because they wanted to do more. This last house is one just a nice example of going from standard efficiency furnace. Again, the consideration of the air coming in the bottom of the furnace there. Over on the right, you can see we lifted up that air handler. So we put it on a base cam so the air can come in the bottom, flow upwards, and work really nicely with a communicating heat pump system. Here's kind of where the rubber meets the road for a lot of people making decisions about these systems. And, I'm putting numbers out there that, obviously these are just to give you some idea of possible comparison amounts. And this would be for maybe a mid-size system. This isn't. So just to help give an idea, if you had a decent existing furnace and you wanted to add air conditioning, and we don't have to reconfigure the whole mechanical space, we can just add a coil on top of an existing furnace, and it's pretty straightforward. An installed cost of $8,000 might be a fair expectation. If you wanted that same in a heat pump, $1,000 more. And so this might be a 15/16 SEER AC, and the same over here, 15 for this single stage heat pump. In that case, I'm going to talk to people about the advantages of an inverter driven, going back to the comfort and efficiency discussion. And that mini split style heat pump that is so small and so quiet really has a great advantages. And you're up to, say, 11. So the top is adding to an existing furnace. And down below,
Zach, can I interrupt for just a second? Because I think this is really interesting. So I just want to make sure we're understanding this correctly, because I think this AC to heat pump comparison is really important. So you're saying this middle scenario is kind of like a really basic heat pump. Now, you said it was a single stage. So it's going to provide some heating in the shoulder seasons, but it's not going to do what a really sophisticated heat pump system would do, but it's still going to take a chunk out of your shoulder season heating. Is that fair to say?
It's going to take a chunk, but I know you've done fantastic webinars on cold weather heat pumps, and some of them were those curves that showed that diagram earlier, where they just continue to offer a lot of heat down to crazy low temperatures. This one's not going to do that.
Right. And then the third example you've got over on the right is more like, this is a more sophisticated heat pump now that you're at.
Yeah, it has all kinds of advantages. They're also great, really small, compact outdoor models.
So I think this is really interesting. So this is the sort of the 3K difference between the air conditioning system that somebody may think they want and a heat pump system that's going to give them a lot more bang for the buck, but it's more expensive. Yeah.
But I find that it's usually, I'm not going to be sometimes what's happening, sometimes the builders have the homes they call AC ready. And in those cases, it's a great opportunity for me to come in and talk to them about adding to an existing furnace because it's a new furnace. Otherwise, I'm looking at this lower row, which is for full system replacements. So if we're looking at a new communicating heat pump, so the outdoor unit and a modulating furnace with the controls, so that might be in the low 20s. And if we go with the full variable speed system, right, a lot of times the nicer units are the one that qualifies for that $2,000 tax credit and makes the difference. So it's really worth it to get the better equipment and all the higher performance. The middle example in the bottom is now doing the mini split style heat pump. So this is my go-to for a small to medium house or a house that has a reasonable load. These are fantastic and a good bit less than a full communicating system. And this is where I'm really looking at how things crisscross and what we want to match up, because I don't want to leave any money on the table for my customers in terms of getting available incentives, tax credits, etc. And then over on the right is an all-electric example. And it comes out to be really the same, right? So it might be, there's a few costs associated to a gas connection and venting and whatnot that go away. And there's about $1,500 of just the parts and the electrician bringing in that backup electric heat. Now, here I want to say that with the new equipment and some of these options that we have, I do a lot of homes where we don't need backup heat. We can meet the load of that building with these heat pumps, and people are super comfortable and they love them and they're great. And so in that, that one, we take $1,500 off of this, and the all electric is the winner from a cost perspective. Down at the bottom, I just made a few notes of, right, because this is a base, these are examples of base costs for installed equipment, but if it's a more involved installation, then the costs will be higher, maybe $1,000 for an nice air purification solution. Or if it's, an equipment change out up in an attic, then that's certainly more work. The last item I want to point out, duct improvements, which can be a lot of work, and can be upwards, if you're replacing ducts, it can be as much as a system replacement. But the last item there, air sealing, when you consider how important the airflow is to the performance of these heat pumps, then spending a little bit of money on improving, the average duct leakage in the US is terrible. And I see it every time I go into a crawl space. They can blow something into the ducts and seal up a lot of that leakage and get a good improvement. So,
hey, Zach, just one, I know we're getting short on time here, but one thing, if you go back a slide here, I wanted to point out, because, as some people are aware, the DOE is considering raising the minimum efficiency standard on furnaces, gas furnace, from 80, where it's been for almost 30 years now, to 95. And I think what we're hearing you say is that, the added costs from changing an older style furnace to a new condensing furnace can be thousands of dollars because of the venting. And, like you say, depending on where the furnace is located, it could be really difficult to vent it to the outside with these new venting systems that are required. So it feels to me like that is going to make a big difference in terms of this equation, because it sort of means that this middle scenario might disappear as an option. And so you're faced with either,
they need to go for heat pumps when they may not have been considering it, and people in the trades need to be understanding really all the advantages of it. To me, that's a little bit of a sore spot, is how many of the others out there seem to be having trouble making adjustments to the technologies that are, I wouldn't even call them new technologies now, right? So, I mean, the heat pumps have been getting so much better in the last 15, 20 years. It's time for people to be looking at
I get Zach and Brian. I do have to wear my timekeeper hat.
Yeah, I
right
think
now.
we're
we're ready to move to our next.
That's it for me, so thank you.
Huge thanks, Zach,
Yeah.
for that presentation. And
Thanks,
look forward
Zach.
to
That's
having
fantastic.
you on our Q&A. But why don't we turn
We'll
it
do
over to
the next one.
Thanks so much.
Sorry, I lost my unmute button. Can you see my screen?
Yes.
Good. Okay, thank you. All right, thanks for having us today to talk about our study on greenhouse gas emission impacts from the electrification of space heating. And I'm here today with my colleague Superjeet. So the goal of our study was to develop a methodology and identify all the factors that contribute to emission impacts from different space heating approaches. And so what we're going to show you here today is comparing an all-electric heat pump to a dual fuel system to a gas furnace. And I also just want to recognize our sponsor, the Natural Resources Defense Council. So what we're trying to do here is we're trying to forecast over 15 years the total global warming impact, those emissions for a gas furnace versus a heat pump. And all the details of this are available in a couple of papers that we'll reference at the end here. And what we're going to show you new today, not in those papers, is a follow-on analysis we did to look at for the heat pump, what happens if it's all electric versus dual fuel. So we're going to run through the methodology today. In the interest of time, it's going to be a little quick, but again, we'll have those references for you at the end if you'd like to go read all the nitty-gritty details. And then we'll show you the results and some discussion points. So what's the situation here? What are we dealing with? So what we're seeing here is the electric sector is slowly decarbonizing as we bring renewable resources onto the grid. So the yellow and brown lines are the carbon dioxide emissions from residential and commercial retail electricity sales. And so you can see here that that peaked in around 2006. So we're seeing those emissions drop over time. But we're seeing the direct emissions, meaning combustion on site in the residential and commercial sectors, essentially stagnant. And so heat pumps are an opportunity to switch from on-site emissions to electric grid electricity source. Okay, I'm going to pass this over to Superjeet to talk about the methodology.
Thanks, Teresa. So going over the methodology briefly before you dive into the results for the analysis, as this is a simulation study, it's important that we go over these inputs and the models. But as Teresa mentioned, most of this information is available in the publications. But I'll go over this real quickly for the folks interested. We did this analysis for two building types. One is this residential home, and other is the medium office building. For home, we modeled two different equipment types, and it has two floors. It's a single equipment for both the floors. It's one gas furnace, and another is a heat pump. And for this study, we also added the dual fuel heat pump to compare. For the office building, it's a 3-floored building, which has, for each floor, there is one core zone and 4 perimeter zones in there. And it is the perimeter zones and the core zone are served by VAV, variable air volume boxes, which has got resistance heating inside of it. We simulate rooftop units for this office building model with a gas pack, which is the gas furnace, and the all electric RTU for this. We do not do the dual fuel analysis for this very building. Next. So looking at all the emissions that can possibly come out of those two buildings, we have the first 3 are the end-use electricity emissions that are applicable for these two equipments. The air handler fan, which is recirculating the air in these buildings, are applicable for both the heat pump and the gas furnace. The compressor end-use electricity is only for the heat pump. The end-use electricity for electric resistance strip heat, that's applicable for the heat pump, the backup with all electric heat pump, and also the office building, as I had mentioned, because for gas furnaces, as I had mentioned, because it uses a variable air volume reheat boxes. So that's a necessity for this type of model. We look at the end-use natural gas conversion. And that's for heat pump with dual fuels, that's we account for that. We also definitely account for the gas furnace from the gas furnace. There has been a lot of people skeptical about the refrigerant leaks from the heat pumps, and that we also account for that from the heat pump side. We look into also the fugitive emissions, leaks and so forth from the grid, and also the end-use natural gas that I'll talk about in a bit. And finally, you also look into the natural gas, the behind-the-meter natural gas leakage that's applicable for the dual fuel heat pump and also for the gas furnace. The last three are we demonstrate them in 100-year GWP, which is the global warming potential, a metric that is used to compare these gases for the global warming in comparison to carbon dioxide. Next slide. So just very quick overview. This is for people who are curious. This is again how the sausage is made and how we do the analysis. We first do a building energy model. We use that data and loads to post-process with data and emissions data and compare that simulate that. Then we will do some visualizations to get the regional impact and do population weighting and everything to make it more reasonable. Next one. So geographic locations wise, so we wanted to find a good representation of the entire US. So we picked 99 cities and we used TMY3 weather data for each of those cities. We used the 2019 census data for the county population weighting factors. And then finally, we used the show the results as county population weighted averages for the 6 regions, as you can see in this plot of the entire US. So that's it. Next. The equipment. So that's another big thing that comes up quite a bit is what type of equipment are we comparing between this gas furnace and heat pump? The gas furnace we are comparing is the top of the line 96% AFUE furnace, condensing furnace. We also account for the fan electricity that goes into the furnace. The heat pump is a variable speed heat pump that we simulate, which has a HSPF of 10 and COP of 3. And these are numbers like, before the new metric of HSPF 2 and CR2 came in. So this is I would say an average furnace, average variable speed furnace, and there are average variable speed heat pump, and there are better heat pumps available for cold climate operations. But we just wanted to compare an average variable speed to get an idea. The capacity ratio can be seen as the heat pump capacity delivered over the rated capacity at 47 degrees Fahrenheit or 8.3 degrees Celsius. And as you can see here, the COP is round about a little above 1, and the capacity ratio is about half when the outdoor temperature reaches 18 degrees Celsius or 0 degrees Fahrenheit. At that very end point, the heat pump switches to fully electric backup, or in dual fuel case, the natural gas backup. But in the electric case, it also does support the heat pump when the heat pump is not able to match the load of the house. So that's it. Thanks. Next. So for the electric grid emissions, we use the NREL Cambium 2021 long-run marginal emissions rate. And the reason we picked long-run marginal emissions because it's calculated from the mixture of generation that would serve a persistent change in the end-use demand. And it takes into account some of the structural changes happening to the grid to bring in renewables. And this is different than the short-run marginal emissions rate, which some of the studies have used, which is looking at the marginal emissions when a new load is added to the current or existing grid. We get the hourly forecast of this from the per state, and we simulate simulate that with the heat pump load factors. To give you an idea of what it looks like, this is a snapshot of average emissions from year 2024. And we are showing this as a metric of kilograms of CO2 emissions per megawatt of electricity generated, per megawatt hour of electricity generated. And you can see that it varies from 256 kilograms per megawatt hour to 620. And to give you an idea, if it is a coal power plant, it's about 1,000 kilograms per megawatt hours. And if it is a natural gas power plant, it's about 400 kilograms of CO2 per megawatt hours. So everything falls around that. And you can see the west of the US is a lot more cleaner than the southeast part in 2024. Next. So lastly, the looking into the fugitive emissions, that's like easy to overlook. We take into account increased refrigerant charge when somebody with air conditioner switches to a heat pump. That's because based on the heat pumps and models and air conditioners we saw that increased charge is seen in when manufacturers switch from air conditioner to a heat pump. So we take that into account in our refrigerant leak calculations. And the refrigerant leak equation is shown here, which predicts all the emissions to the end of the operational life of the equipment. And if you look at the overall 15-year operational life that we simulated in this, the refrigerant leakage is expected to be more than 100% of the total charge of the unit throughout the life. We also account for a change in refrigerant due to the ratification of the Kigali Amendment and the AIM Act in the federal level. And we see that because of those two policies, there will be a change from HFCs, which is the R410A, most commonly used refrigerant, to R32, which is an example of lower GWP refrigerant from 2026. On the natural gas side, we to account for the leaks, we take into account production leakage, so natural gas production leakage from various states around the US. And we also take into account the post-meter leakage, which is behind the meter of the customer. As you can see here, the production leakage on the west is surprisingly higher than the east side of the United States. Now I'll turn it over to Teresa to talk about the results.
Okay, thank you. So the first thing I just want to talk about today is the question, what did the models show in terms of how frequently the heat pump is running versus how frequently the backup heat is running? And so that's these dark orange bars. So basically you can see that it changes depending on climate, as you would expect. So like in the coldest Midwest climate, where the heat pump is meeting the heating load, providing about 80% of the heat. Whereas as we get to the Southwest, the heat pump is providing more than 95% of the heat in the home. It's a little bit different for the office building. And the reason for that is that the office building has a deep setback at night, right? The temperature, you said thermostat setback, and we don't get any heating at night. And so that has to recover that office building in the morning. And so that's where the backup heat comes in. And so you can see that, like, for example, in the average US is more like 80% of the heat coming from the heat pump. And so this just gets us to start thinking about, like, what are the control strategies for heat pumps, and are there ways that we can control them to provide more of the load? But we're just simulating typical controls here, nothing fancy, and this is the result that we get. So when we think about dual fuel or some other sort of electric resistance backup, or we're talking about how that heat pump is operating somewhere between 5 to 20% of the time. That's what we're worried about. What's going to happen in that time frame. Okay, and so there's a lot of information here, but this is our emission projections for a total of 15 years, the system operating for 15 years. And so on the left here, we have the results for the house, and the first 3 bars of the gas furnace. So the emissions for the gas furnace, and this is normalized per unit of floor area. You can see that the combustion of the gas makes up the biggest chunk of the emissions. The production leakage, the basically drilling for that natural gas, and the methane emissions associated with that is the next chunk. And then we also lose some behind the meter at the home. When it comes to the dual fuel system, we burn a lot less natural gas. And so now we have the emissions associated with the electricity to run the compressor, this light orange bar here. We still are burning some methane on site, so that's the combustion. And then we still also have some gas leakage as well. There's a new bar, which is the green bar. That's the refrigerant, the global warming impact associated with the refrigerant leaks. Even though we assumed a pretty substantial amount of refrigerant is leaked, you can see that it's like kind of on the margins, right? It doesn't really turn out to be that big of a deal, and comparatively to these other sources of emissions. And it gets better with time as we go to the lower global warming potential refrigerants. The all-electric heat pump looks pretty similar to the dual fuel heat pump, except we trade these on-site methane emissions for the emissions associated to run electric resistance backup heat. Now, I know we've talked about that there are solutions that might be more efficient than electric resistance backup heat, but we did not simulate like the best available heat pump technology. We simulated widely available typical heat pump technology. And so, but if we look sort of on average across the US in terms of total emissions over 15 years, they drop over time, but essentially it's a little bit of a wash between dual fuel and all electric. I just briefly want to talk about the office building. What's interesting about the office building is that you can see the emissions per unit floor area are like an order of magnitude lower than the house. And that's because an office doesn't have as much perimeter to the building compared to the floor area. And so you just lose a lot less heat per unit of floor area. What's also really interesting about the office is that these refrigerant leaks become a much bigger deal in the office building. And that's because we designed the heat pump to meet the peak heating load, right? But the heat pump doesn't run as consistently as it does in the house, and it doesn't provide as much heating. And so although the refrigerant leakage just becomes a much more important part of the story because the refrigerant is there, whether it's being used for heating or not. So now what I've done here is we've just rerun the calculation where we calculate the savings relative to a gas furnace. And so basically now we're looking at this by region. And so what we can take away here is the green is the dual fuel savings. So like if a heat pump got rid of all the emissions, that would be 100% savings. And so the green is the dual fuel scenario, the blue is the all electric heat pump, and the purple just shows the office building. And so what you can see here is that, for example, the Pacific region does much better than like the Midwest. And that's for two reasons. One, the climate is more mild, and two, the source of electricity has more renewables. And then there's a couple of like anomalies. We can see here that in the office building, we actually project that there would be a negative consequence from an all-electric heat pump installation today. And that's because of that issue of the refrigerant leaks, like in a climate that's mild. So adding all that extra refrigerant to an office building is questionable. And so that's where this refrigerant transition becomes really important, is in this building type. And that's happening, that's imminent. So we see then with time that the problem essentially resolves. I just also wanted to show here, Brian asked me to include results for Oregon specifically. And so I'm showing Portland and Redmond, and you can see that these cities are essentially some of the best in the US in terms of the expected savings you would get from heat pump installation. Again, it's a little bit of a coin toss on dual fuel or heat pump, all electric heat pump, and all electric wins slightly in Oregon.
Teresa, can I interrupt for just a minute? So is it fair to say that if you were installing like a really sophisticated heat pump system with more efficient equipment, the blue bars would be slightly higher, but I guess you could also say the same would happen if you were installing that same more efficient equipment with the dual fuel system too. So would that mean that both bars would go up if you were installing better equipment, or is there a difference there you can see?
It depends on what happens. I mean, the differential we're seeing between the green bar and the blue bar is just the difference in the backup heat. So in the green bar, it's a gas furnace. In the blue bar, it's an electric resistance heater running. So if you can get rid of that electric resistance and use a more efficient heat pump for, like, essentially eliminate the need for backup heat, then your blue bar would get even better.
Thank you.
So conclusions here, we forecast significant emission reductions in all regions. The Pacific region is particularly attractive for heat pump installation because of our climate and also because of our access to renewable electricity. As heat pumps become more and more adopted, we have to start thinking about, like, how are these controlled and how are thermostats working to reduce this recovery that we need in the house and how we recover. I've seen questions in the chat about this, and I'm just gonna be really blunt, like, we're not addressing operational costs here. They vary widely by location. And it's also pretty difficult to project what electricity and natural gas prices are going to look like in the future, and what those prices look like are likely going to be impacted by adoption rates. Because as people move off natural gas, the cost of maintaining that infrastructure are going to be borne essentially by the remaining customers. And so this all gets very tricky in terms of cost projection. Also, like, building off the last question, we are modeling, we're modeling a variable speed heat pump. It's not the least efficient heat pump out there, but it's also not the most efficient. There's a current challenge going on with DOE called the Cold Climate Heat Pump Challenge. Their target for that challenge is 40% more efficient than what we modeled. In the meantime, rubber meets the road. Any heat pump that goes in is a good heat pump, I would say. Right. So if dual fuel is what gets it done, it's a step. It's definitely a step in the right direction. The little asterisk I want to put on the model is that we did not assume any leakage in the transmission infrastructure. So, like, all the piping that runs through the neighborhoods, because the data shows that that's small right now in comparison to the production leakage and behind the meter leakage. But as we pull homes off the natural gas infrastructure, that infrastructure is still going to have to be pressurized all the time. And so those transmission leaks are going to start to become a bigger and bigger, are going to have to be considered, because even if we use less gas, if we keep the transmission system pressurized, it's going to continue to leak and it's going to become more significant. And that's all I have.
That's great. There was, Teresa, there was one question about the difference in the bars that you were showing by year and why they change. And that's basically because the grid carbon emission intensity is changing over that period. Is that correct?
Yes. Well, there's a couple of changes. One, the refrigerant global warming impact reduces. So we use a lower GWP refrigerant as time goes on. And then the other thing is the grid gets better. Yeah.
Thank you.
And how much better are we assuming, Teresa, or does NREL assume from your study? Do they assume that a completely carbon-free grid by a certain date? What are the assumptions there?
We're relying on the NREL analysis, and they have different scenarios. We're using their low renewable energy cost scenario, which the answer is no, it does not assume, there's no like carbon-free grid assumption. It assumes that like the lowest cost renewable sources are used to meet the demand.
Gotcha. So, and I seem to remember too, this was done before some of the more recent legislation, like Oregon just passed their, 100% clean law, for example, which would affect that slightly, but
it was based on legislation that was in place as of June 30, 2021. Gotcha.
Thank you.
So yes, it can get better.
Yeah, fingers crossed it does get better. Okay, great. Why don't we invite folks on camera and Teresa, if you want to stop sharing, that's great. We have about 10 minutes for Q&A, and we got to let our panelists go. But Brian, do you have a good question to kick us off?
Wow. I mean, first of all, thank you all of you so much. And Chris, welcome to the show here. I guess, you know, I have to say, I was a little surprised seeing this data. I was expecting to see bigger differences between the cost of installing a dual fuel system versus an all electric system. So it sounds like those things are closer than I expected. And also, I'm very surprised to see the emissions being so similar. So I guess, you know, I got a question for, you know, I'm not sure who, maybe I'll start with you, Teresa. Like, I mean, if you give us what you see out of the, what conclusions you draw of this about like the short-term role of dual fuel? You said it, you know, any heat pump's a good heat pump, but if you're thinking long-term, how do you feel like dual fuel fits into the picture long-term? What's your take on that?
I mean, I think in residential particularly, there's in most cases, except maybe the coldest climates in the United States, there's really no reason that technically that an all electric solution won't work. So there's just going to be, it's going to come down to like practical considerations in terms of like, does the, you know, cost of installation, it's going to come down to other decision-making factors that are not engineering based, right? It's going to come down to what people are comfortable with, what they know, what they don't know, what's on the truck, like the day you need heating, right? Like what can you get? You can't buy something that nobody's selling you. But I think long term, you know, the role of natural gas is going to shift more towards sources that are harder to electrify. Like right now we can electrify residential, and in my opinion, we should. And you know, and yeah, that's all.
Zach, it looked like you wanted to add to that.
Just in total agreement.
Okay, great.
Just nodding along. Yep.
Yeah, awesome. Well, a question maybe for Zach and Chris. You know, someone was, you know, we talked a lot about the upfront costs for dual fuel systems versus all electric. What about the maintenance costs? Yeah, you know, I think of the plug-in hybrid electric versus the all electric vehicle. And the plug-in hybrid, you've got more maintenance because you've got the gas system and the electric system. Is that comparable to the dual fuel heating versus all electric?
They're going to be pretty comparable. I mean, I'm thinking that any system, if you had, say, furnace AC, then you still have refrigerant there. I mean, that's you're just not getting the heat pump functionality, but you have all the same system components.
Hey, Chris, I got a question for you because, you know, I love the insider view. We got a chance to give someone from the really deep in the industry who's sort of seeing a little bit what we don't see in the market in terms of what's happening with, you know, product development and all that sort of stuff. So, you know, I know you're a heat pump geek, but can you just say a little bit about, you know, what you see the manufacturers of this equipment, what are they thinking about all this stuff? I mean, where are you make, because to some degree, you know, the manufacturers have to make bets on what they think people are going to want. And so, you know, that translates into R&D dollars, where you're spending your R&D dollars, and, you know, what you stock in inventory, all these things. Can you just talk to that about us? I mean, you know, because you got a view that most people don't have in that regard.
Yeah, so I mean, you're right. It's really interesting. I can tell you that just even myself, it's always about coordinating how much equipment is in what distribution warehouse network and how we plan how to bring in boxes and deliver them out to what people need. Yeah, I can just tell you from Carrier Corporation, I mean, you know, they know that, I mean, it's definitely, everybody knows that there's a transformational shift and electrification is, you know, absolutely happening. You can see that with, you know, for example, like Carrier alone just purchased, you know, an entire entity called Toshiba, you know, all their factories, plants, patents, people. I mean, the chess pieces are being moved, you know, in that direction for sure. But I can just tell you in the Northwest region, my 6 states, you know, I can just tell you our warehouses are drastically filled with different equipment, you know, even, you know, Brian, I've shared with you before, even like 2 years ago, 3 years ago, 4 or 5 years ago, how many furnaces we've sold versus how much few less furnaces we're selling now. It's pretty substantial. Some of that's code driven, you know, in the state of Washington. I saw some of people's questions popping up here, and, you know, the new code coming in for Washington for the 2021 code is like, the top code credits for houses is no supplemental heat, no gas furnace. It's all heat pumps. You know, somebody was asking about that. Oregon has a little bit different codes. So sometimes codes driving this. People are definitely, I bet you if Zach was, you know, he'll jump on after. People are asking to fuel switch every day. I mean, it's dramatic. I've never seen anything like it. So, I mean, when you and I talked about dual fuel, and for the people who are watching this, it's just dual fuel could either sound very scary, or maybe it has an intermediate solution to help with the process of forward momentum into electrification. You know, Zach gave you some really practical boots on the ground reasons why sometimes people, you know, they'll call Zach in climate control and they want to save the world and they want to go all electric. And then when they find out how much it costs, a lot of times they're like, you know, I didn't want to save it that much. You know, that happens a lot. And people with the most noble intentions sometimes can't afford it. So sometimes it leans, maybe you grab that 80% venting, that B vent, but you get them into a heat pump, you get the disconnect upgraded outside, you get that forward momentum. And I can test that if you get them going down the heat pump, you prove out that these systems, which, you know, from Carrier, we pretty much, I don't care if it's Canada, I have customers that do heat pumps in Alaska. There's no region in the United States that we cannot do a heat pump solution and pretty much handle it with just heat pumps alone, really. Things have changed so much. There's so much urban legend out there about what heat pumps can do, but a dual fuel solution that is there to protect people. Some people do it for security and safety. Some people are just doing it because of cost, but I'm glad that Zach kind of presented it the way he was so that people would know, well, you know, some contractors are just going to throw it up there with a 40-degree lockout. Well, that's way different than what Zach was describing, which was it's a heat pump solution either way. And it's all about handling that last little bit, you know, and how to get people moving in the right direction. That was a long answer. I'm sorry, but
that's really good. I mean, Joe, do you have another question? I want to follow up on that set point temperature thing.
Yeah, I do want to get to the set point too. I know Teresa and Superjeet do need to run. I wanted to give them one last question, then maybe they have a bunch of events today, so we're so appreciative of their time. Maybe one more question there, and then we'll go to the set point. I have the thought, Teresa and Superjeet, about when you were talking about the commercial buildings and changing that or turning the heat lower at night, and how that had a big cost on emissions. And our user David said, has there been any planned feedback to Ecobee or Nest to modify setback and recovery opportunities for dual fuel systems? Is the message here that, you know, for heat pumps, you set it and forget it, you don't turn it back at night because of the effect on emissions, or any thoughts on that?
Yeah, so what I was getting at was that, so if you're operating a dual fuel system and the backup is gas, then it doesn't really matter. But if your backup is electric resistance heaters that are low efficiency, now this starts to matter more. And the problem is that in terms of, so the ideal solution, and that's what we're working towards, and we are doing research on this, and we do have partnerships with manufacturers, like you mentioned, control manufacturers. And so the way that this is all moving is that our thermostats will become more intelligent, right? And they will automatically communicate in terms of like real-time pricing, real-time emission signals. And this is all going to get a lot smarter. It's just not there yet. And there was another comment in the chat about like, well, if I want to like operate the best I can today, like it would be very difficult because we don't really have insight into like what the utility is doing in terms of how it's managing the grid at any given moment in time. So that's really difficult to do. But there's an entity out there called Watt Time that essentially is tracking real-time emissions. And so anyway, I think all that's coming. Stay tuned. Our website, I'll put it in the chat, but we have a section on load flexibility if you want to like follow what's happening there.
Great.
Yeah, thanks. And if you two need to drop, we thank you.
Yeah,
so
we
much.
appreciate it.
Okay.
And thank you so
Thank
much
you.
for being here today and for the little extra time. We really love what you guys are doing. So thank you both very much. Superjeet, thanks so much for your time today.
Thank you.
Okay,
Brian.
thanks. Bye.
Chris and Zach, I got a question for you about set point temperature, because it feels to me like, and Chris, you sort of touched on it there, that, you know, if you're, I don't want to throw any installers under the bus here, but if you're not like really thinking about this and if you put the set point temperature at 45 or 40, you know, it feels like you're squandering a lot of really good opportunities for efficiency and even comfort potentially. Is there a way to I mean, what's the answer there? Is it just that the installers have to be smarter, or is there something that about consumer education that could be part of this? Or is there potentially even a policy that says, no, you have to set it at X? Or do you guys have thoughts about that? I mean, how do we maximize the efficiency of these dual fuel systems that go in?
Well, I'll go first, Zach, and then you follow up. I will tell you this, that in the end, for everyone who's listening, I mean, the homeowner, you know, it's your home, it's your system or your business. You can ask to have the lockout, you know, where you want it to up front, you know, and it's up to the person who's consulting to advise what outputs of heating the system makes at those temperatures, you know. So the one thing is, you know, if you're talking to somebody who is just adamant about that, that should already be a bell going off in your mind. Most really good contractors out there, you know, it's a very, very old school thing. 40 degrees is a very old school thing. That would already be maybe an alarm flag to maybe I should be talking to more people or do a little more research. I would say that, you know, you at least want to get into the low 30s for a lockout, sometimes even much lower. Now sometimes we'll have customers that just say, I want a low lockout, or no, you know, they want to go as far as we can, and they'll walk you through it. So definitely the homeowner or the business owner should be talking about it, and you can demand that. I mean, it's not like the installer is, you know, it's your home now, but any good installer should be listening to the homeowner. Somebody should have already consulted them up front, but it's not like it's mandatory, has to be a certain lockout temperature. And that's when you come down to those different philosophies, you know. If you know how it is, it's just, I'll let Zach talk about what climate control does, but what we love is we want our comfort advisors in the Carrier Bryant network to look at the product data, do a load calc in the house, and try to figure out what exactly it needs so that you can make exact informed, you know, decisions, and try to go with the smallest equipment you can with the longest run times. And with the cold climate heat pumps, we're all about those, and we want to use the benefits. That's like having a Lamborghini in in the garage, and you're only going to take it out and drive it at 30 miles an hour. You know, it's a waste to set a lockout at 40 degrees.
So Chris, and just so folks know, the lockout, the switchover temperature is when the heat pump kicks it over to the gas furnace and the gas furnace turns on. And
exactly right.
Zach, did you have anything you wanted to add to that, Zach?
Yeah, I'm going to jump in with a real simple idea on our thought on that topic. Is, you know, I did sort of a long explanation that could say, well, here's all these reasons why you would have, you know, maybe this lockout temperature, but you could also get your system installed and literally shut off the gas valve to your furnace, you know, set your thermostat to say run in heat pump mode. Use it. And that heat pump is going to tell you when your backup temperature is, going to give you a real idea of what that temperature, your crossover temperature is.
Yeah.
You feel like,
at the point where the house is too cold, Zach. I mean, at the point where you're too cold in the house, then you know that.
There you go. There's your temperature.
That's interesting.
Yeah. But just for a general idea, I mean, Chris, I heard you say, I mean, does it depend on the model? Is it, you know, low 30s should we be encouraging folks? We even go, I mean, Zach, we saw 26 there on your example.
I want people to be covered completely with those heat pumps. But here's the main point, or the thing that's been in my mind in this webinar is, and I was wanting to show in my model the diagram of a heat pump operation that the house is the first piece and the ductworks are a critical component. So when people talk to me and they say, well, you know, I got these other bids, and if I went with other equipment, they say I won't need a backup. You know, it's like, the equipment is delivering. We have fantastic equipment options, but there's some other factors that go into this discussion. And so if you look at it from, you know, this broader home performance perspective, hey, you know, do some air sealing and do some insulation. And now your load is, you're attacking it from another angle, right? There's some low hanging fruit there, and fixing your ductwork. That comes to my mind in terms of, are we going to get to all electric systems? It's not well, if I just shop around and find a different box, it'll do that much more.
So it's not it's not just the heat pump, but it's the entire system.
I think that's a good point.
So the lockout, we call it a droop setting. Most of the time in the industry term for it is droop setting. I don't know, but balance point or whatever, just so you know, with the all electric system, everyone who's on here, you can actually have supplemental heat, or it'll decide not to come on or bring on a little bit to help. But with gas, it's got to be one or the other. And once you pick that lockout, it switches over. And so that's why we're wrestling with that balance point of switchover. And I will tell you, most manufacturers have to recommend something. At Carrier, they do a recommendation of 35 degrees. Now, that's a very generic, they just picked it. You got to pick something, but we always try to teach and advise that you can adjust that based upon the output of the equipment. If you have like larger 4 or 5 ton size heat pumps, they're not quite as performers as 2, 2.5, 3 ton type, where that's really that sweet spot on these compressors. So every system in every house really is a little bit different and has to be looked at. So, but whether it's Trane, Carrier, Lennox, I mean, they are going to always have something. Now, I don't think anybody's doing 40 degrees anymore. Most of the time it should be lower. That really is that's a 30 years ago type of thing.
Thanks, Chris. Yeah, I think that's a great point on the your point on the heat pump with the electric strip backup. I know my family's Cleveland house, we have a heat pump with electric strip backup, but at that point, the electric strip is just kicking in here and there when it needs a little boost, but the heat pump is still running. But with the gas backup, you have to shut off the heat pump and go to full furnace. Yeah.
Right, exactly. So it's a little bit of a different limiting aspect to it.
Hey, question real quick on the, somebody asked about new construction. Is there any point to put in a gas backup in new construction, or is it safe to say that a heat pump with maybe electric resistance backup or just heat pump alone is the option, the viable option there?
So I am not involved in new construction. I'm a residential retrofit person, but I'll take a stab at answering that. Is the construction process is to build a home to it's normal. If you do a custom home, it's a different story, and there absolutely you should be designing the home with the load in mind, and you should put in good, there just should be no backup needed. And so because you have control of it and you're thinking about this, production builders, a different story where they're yeah.
But even with new codes, for insulation and windows, and I would assume, I don't know about ducting though, whether the codes on ducting have changed, which would mean that a new built home would be more likely to have ducts that would be adequate. It would seem like all those things would make electrifying a new home a lot easier than electrifying an older home. Is that true?
So it is true. I mean, one of the things that we do, we have a lot of we do a lot of work with builders, regional builders, national builders, and Zach's with a retrofit company. We do a lot of companies that do new construction. I'll tell you this, each state's a little bit different. California, Washington's got the most strict building code in the country. California has what things they're doing. It's always a little bit different, but I will tell you the trend absolutely is heat pump. And even now we're starting to see builders are realizing, they used to feel the pressure of like, I have to put gas in this neighborhood because that's what people want for high-end home. That's really changing. Now they're starting to realize like, cold climate heat pump, this is a buzzword I'm hearing. We're seeing more and more builders go, you know what, we're doing this in Washington and Oregon, the rules aren't the same, but we're going to match them up both. And we're seeing a huge trend on heat pumps. The other thing is, we're seeing a huge trend on not doing ductwork at all and doing, traditional mini splits systems where everything is located within the conditioned space for high wall heads and low floor. So the trend is, it's definitely it's a massive curve up in terms of heat pumps. I think it's just the numbers don't lie, but each state has different code, and code mandates what gets put in there. So it's a little bit different in each state.
Hey, I know we've gone over time here. We should probably wrap up. Joe, do you have any last questions, or should we wrap?
I think that's been great. Just a huge thanks to Zach and Chris for their time and their presentation on this really important topic.
Yeah, I would echo that. And thanks again to Teresa and Subhrajit, who aren't here with us now. But and thank you all for tuning in. I hope this was helpful to you. And of course, it's always hard to have one webinar that answers everyone's questions. I mean, if you've got additional questions that we didn't answer, maybe some just simple practical things and we were too deep in the weeds, here potentially for you. Feel free to reach out to Joe or I. If we can't answer your question, we can send you to someone who can. And as we like to say to all of you, good luck with all of your electrification projects. And hopefully Electrify Now can help you to get where you want to go with your own home. Thanks very much.
Thanks, everyone.
Thank you.
Bye-bye.